So continuing, sort of like an offshoot or something we're able to do now is, since we can factor quadratics and solve quadratic equations, we're going to be able to look at how to solve linear and nonlinear systems. So before, when we were doing linear, we had, our parallel lines, and we knew that there was no intersection. We just had, two lines with different slopes, and we had one intersection, or we had that line that was the exact same thing, and we had infinite solutions. So when we find this nonlinear, it could be anything, but I think we focus here on a quadratic equation and then a line passing through it, and the solutions would be these two locations right there where the line passes over the quadratic equation. Or even if you had something that was possibly cubic, you might have something like that where you had a straight line going through a cubic function, and you would end up with three possible solutions, or maybe just one solution. But that's what we're talking about here, is the being able to calculate those solutions of nonlinear systems. So looking here, solving a linear and quadratic system using substitution. So in order to do that, we have two variables, your x and your y, and then of course part of substitution is eliminating one of those variables to where we have just all a series of y or x variables, so we can solve, because you can't solve for two different variables at a time. So solving this system, we want to solve the equation number 2 for x. So what we're trying to do is we're trying to solve everything in terms of y. So x is equal to y plus 1. So we just have manipulated this to find out that x plus equals y plus 1 is the equivalent. So now we can take right here with this x and substitute in x plus 1. And that's what they've done. They have, for x, they've substituted in x plus 1 equals this. And then doing my inverse operations, they have gone ahead and they have subtracted y, and they have subtracted 1 from both sides. And they have come up with just 2y squared plus 2y is equal to 0. And then they're able to factor out a greatest common factor, which is 2y. If we factor 2y out of here, we have y left behind. If we factor 2y out of here, we have 1 left behind. So now we can solve those independently, where you have 2y is equal to 0, or you have y plus 1 is equal to 0, and then dividing both sides by 2, of course, y is equal to 0. Subtracting 1 from both sides, y is equal to negative 1. So we can calculate the values of our intersections, our solutions, the y values, and then just plug that information in. So when I have one solution, when y is equal to 0, x plus y plus 1, so x is equal to, I said x plus, x is equal to y plus 1, y is 0, right? So 0 plus 1 is 1. So the ordered pair there would be 1, 0. Substituting in negative 1, we have negative 1 plus 1 is 0. So x is going to be equal to 0, so I have 0, negative 1. So being able to find that, in this example, we're thinking we have a line crossing over a quadratic equation. We were able to calculate those two ordered pairs. And that is, we're just taking linear systems and moving up just a little bit. Now we have nonlinear systems and understanding what we see and how to interpret those results. So solving using elimination, same method. How did we do that? We used elimination to get rid of one variable. And in order to do elimination, we had to make sure that we're lined up, right? So my equal sign's not lined up, so we want to manipulate this equation, moving it around to get y and my constant on the same side as here. So as we do that, and we have x squared equals y plus 5, negative x equals negative y plus 7, and then when we combine like terms, we bring down our x squared, we bring down our negative x, and then equals 12. And then they go ahead and they start processing it to factor a quadratic. They subtract 12 from both sides, and now we can factor x squared minus x minus 12. X minus 4 times x plus 3 is equal to 0. Doing your inverse operations, of course, adding 4 to both sides, subtracting 3 from both sides, and we come up with our x values. Plug those back in, and let's see here, x is 4, so negative 4, let me add 4 to both sides, and then y is going to be equal to 11. And then here, that is going to be, let's see here, that's going to be a positive 3, so I subtract 3 from both sides, and that's going to be a positive 4. So we're able to calculate, once we found the x value, we were able to turn around and put it in and find the y value. So that is using elimination. So solving this system now, creating a system and understanding that we have this equation, and I am trying to find out, there's two different ways to do this, but the way they're talking about here is I'm going to take this portion of the equation and make it equal to y, and then I'm going to take this portion of the equation and make it equal to y, and now I can do exactly the same thing that I did up above, okay? Create the system, then graph the system. So as I graph them, I can turn around and identify that there is an intersection right here. There is an intersection right here. And they do identify that this appears to be 1, 5. This appears to be 5, 21. And then that is going to be the solutions there. So here, doing the same thing, if I were to graph these, I would definitely want to say, hey, I got y is equal to, and I'm going to put it in y1 on my graphing calculator. Y1 is equal to 2x plus 11. Y2 is going to be equal to x squared plus x minus 1. And now I see if we can go ahead and graph those and come up with the solutions. Okay, so I've taken a couple of pictures here to identify. I went ahead and plugged it into the calculator. So I put in 2x plus 1, I put in x squared plus x minus 1. And when I graphed it, this is what showed up. Now I can see here that one of my solutions appears to be negative 1, negative 2, negative 3, 1, 2, 3, 4, 5. So it looks like one of my solutions is negative 3, 5. Now I can't see the other one because it is up there somewhere. So what I can do is I can turn around and look at the table. And here, here is the table. And if you'll notice, the blue function, here's y1, here's y2. I said negative 3 and 5 was my solution. So sure enough, my y values, my x's, and then my two y values are 5. So yeah, that's my solution for them. And then if you come down here, we can see that when x is 4, both of my y values match up. So my other ordered pair, which is off the screen up there, is actually going to be 4, 19. So that is going to be the solution. Those are my two solution points. And again, being able to recognize it within the table, understanding what's going on, making things a lot easier for us. Okay, so understanding that. So the two x values, the solutions, or my x values, would be negative 3 and 4. All right, so now doing the same thing here. Solve this linear quadratic system by graphing. A software developer determines that her company can model their revenue from a given product in hundreds of thousands of dollars given the unit price of the product X in dollars, and the function revenue is equal to negative 0.1 x squared plus 4x. Create a linear quadratic system and solve it graphically to determine the price for which the company will earn 4.7 million. Okay, 4.2 million. So create the linear and quadratic system. We obviously have, this is my revenue, And then my other line of revenue, we want the revenue to be 42 million. Or in this case, we want it to be 4.2 million, but in terms of 100,000, it would be 42 100,000s. And then so here's R for one system, here's R for the other system. And when they graphed it, it turns out when they graph the system, here is R is 42, because that's what we want the revenue to be. And then this system, this product, this revenue stream, never actually reaches their goal of 42. Never actually reaches their goal. So the graph of the functions do not intersect. So there are zero solutions. There are zero values of x that will meet that. And that's being able to interpret that we can have two solutions, but in this case we only had zero because they actually did not intersect. So looking at this next word problem, let's see here. Engineers want to build a footbridge with steps across a steep valley. They can model the valley with the equation, this equation. I'm thinking the valley arbitrarily would look something like that, right? And then where y is the height of the lowest point of the valley in feet, and x is the distance from where they plan to start the bridge. If they start the bridge 80 feet above the ground, call that 80, right? And want to go down an inch for every foot to the right, what is the point? Then at what points will the bridge start to end? Okay, so they're starting at 80 feet, which would be my y-intercept, and they want to go down an inch for every foot to the right. Okay, so there are 12 inches in a foot. So I'm going to go down one. I'm going to go down 1 inch for every foot to the right, which would be 12 inches. So I needed to turn that foot into inches because I couldn't, I don't want to have inches and feet. So that is one of my equations. The other equation here, this one is modeled. This can be modeled, model the valley with an equation this, where y is the height above the lowest point in the valley in feet. Okay, so in feet. This is in feet, this is in inches. I should probably correct that, because this isn't 1 out of 12 feet. I'm going to convert this to a decimal, so that would actually be y is equal to negative 0.08x, 0.08 feet, plus 80, and we'll see how that works in the graphing calculator. So when I go to check my tables, I put this into equation number 1, this is in our y1 and y2, and I look on my chart here, my tables, there is at 0, there's my y-intercept of 80, so that's where we started, and as I went down, it turns out that the closest we get is going to be here at 78. When x is 78, we're very close to finding our location, so we can see that we're going to be able to narrow it down, but approximately at 70, when x is 78, we will have y is 73-ish. Okay, so that's where we're going to end up, being able to find where this starts and ends. So just looking at that, so it looks like we start at 0.80 and then we end at approximately 78, 73, because that is the point where it has the closest connections. So we could break it down to find a greater decimal, but we're just going to go with the whole number there. Now, looking here, solving the quadratic and quadratic systems, well, now we are in a point where we can make them and factor them, and let's see what happens here. So we're looking at understanding that, hey, the vertex, right? Y equals x squared is the same thing as this, which is the same thing as this, which is the same thing as this. Just understanding that those are all equivalent statements. So here, if we want to turn around and do some form of systems by graphing, and I will say that what they've identified is we know that when we have y equals x squared, typically we open upward or downward depending the characteristics. But when you have x equals y squared, you end up with a side-to-side looking parabola. So understanding that is important. But for the purpose of this course, what we're going to talk about is we're just going to talk about these. Okay, being aware that this is a side-to-side opening, we are not going to actually work with these problems, but you can see that it is possible to calculate your solutions and being able to see them visually, what might be going on, using our table to calculate the data. But for the purpose of this class, we're going to just focus on my y equals x squared, the parabolas that we are used to working with. So here, if we turn around and do some substitution, see if we can work on finding the solutions to these systems. Okay, so as we look at this, I've gone and I've created a system where we have these two systems working together, and I'm going to use the elimination method because we've been given several methods to use. I just thought this would work the best for me. And I'm going to try to eliminate y, and by doing that, I'm going to multiply my top line by -3. So when I do that, it becomes a -3y equals 3x squared minus 15x plus 18. And then when I combine these two lines, I end up with 0 equals 4x squared minus 16x plus 12. Now, greatest common factor, I want to do that first. I divided everything by 4, and what I do to one side of the equation, I do by the other, okay? And I end up with 0 is equal to x squared minus 4x plus 3. So I can now factor that. Factors of 3 that will sum to be -4 would be -3 and -1. So I have x minus 1 equals 0 or x minus 3 equals 0. So it turns out my solutions are x is 1 and x is 3. Now when I plug those back into my equation, I find out that the resulting ordered pairs are -2, so 1, -2, and 3, 0. So those would be my solutions to that systems of equations. So that is one way to approach this. Now, solving a quadratic in quadratic algebraically is very similar to what I just did, right? I just used my critical thinking skills and I used the one that was easiest for me. So in this example, this next example, what they did is they said, we have y, and what I'm going to do is I'm going to do substitution. So for this y, I'm going to substitute this entire expression. So they ended up with 2x squared minus, right? 2x squared minus, and then y was negative minus 1/2 x squared plus 6, and then equals 4. Then they did the distributive property. You know, they had to distribute the sign, and then now that they have that, they went ahead and combined like terms, and this became 2 and 1, 2 over 1 plus 1/2 is the same thing as 5 over 2 x squared. Then they subtracted, of course, 4 from both sides, and that's how they have the -10. So and again, to get rid of that fraction, what they did is they said, hey, if we multiply everything times 2, it's going to eliminate this fraction. So I end up with 5x squared minus 20 equals 0. Now I have a greatest common factor. I can divide everything by 5, and I get x squared minus 4 equals 0. Hopefully you recognize that as the difference of squares, right? Square minus a square. So that would be x plus 2, x minus 2. And the solutions would be as x is plus or minus 2. That would be my solutions. When they turn around and they plug those values back in, what you see is what you get. Plugging in the value of 2 into my equation, I get 4. Plugging in the value of negative 2 into my equation, I get 4. So those are my two solution sets. Okay. Now, I'm not going to go through this step, this last equation, because we're going to do this in class, of course, and we're going to do a lot. But if you do it on your own, what you should be looking for is you should end up with 2, 6, and 2, negative 6. Easiest thing to do, of course, is to substitute in x right there. And then, oh gosh, let's just go ahead and do it real quick. Y squared is equal to negative 18 times 118 y squared plus 72. This simplifies, so we have y squared is equal to minus y squared plus 72. Add y squared to both sides. I have 2y squared is equal to 72 dividing by 2. I have y squared is equal to 36. Square root of both sides, I have y is equal to plus or minus 6. That's how we came up with that. Now, when you plug that back in for y, either one of my equations, you will find out that x is going to be equal to 2. So there you go. That's what they, it wasn't that hard. It had a fraction in it, but, it's well within our skill set to be able to accomplish something like that. So again, we'll do these. We will understand but not worry about these, okay? And with that, we're going to go on and do a little bit of this practice. And so last, you have this quadratic system. Again, we are taking these two quadratic equations and turning them into independent solutions, or independent equations. We have an equation and we turn it into two independent functions that we are able to graph. So when we graph our first function, it looks something like this. When we graph our second function, it looks something like this. And being able to find that intersection point, because the two solutions reside right there. And it's well within our means to be able to calculate that. And then here we go. So it looks like at negative 1/2, our solution is going to be y is 10. At 1, our solution seems to be y is 7. So the solutions to this are, remember, your solution should be your x values. So it should be negative 1/2 and 1. So my intersection points, and then my actual solutions are the x values. Doing the same thing here with this equation, and I'm going to go ahead again and use the calculator for this, separating it into my two equations, being able to find what those solution points and then ultimate solutions are. So we can see here when I put them into the graphing calculator, one equation is negative x squared plus 3x plus 14. The other one is negative 1/4 x squared plus 5. Now my solutions, it turns out when x is negative 2, y is 4. That's one intersection point. And the other intersection point is when x is 6, y is negative 4. And so my solutions are the x values of negative 2 and 6. So there you go. That's being able to understand what we're seeing in our tables and how to create that equation. In class, we'll probably talk about the related function some more and how to solve using that method too. But again, we'll do some practice.